Thank you, Kyle, for giving this opportunity and for organizing the whole webinar series. Thank you all for sitting in and listening. Originally, I really thought I'd give my usual talk on mechanics, on ferroelastic toughening. I thought most of you don't understand it, and it's just appropriate that you finally get it. Then I felt challenged and decided I do something a little bit different. In doing so, I got input from Andreas Woninsland, Mahua Zhang, and from Yingwei Li from Wuhan University. I gave the whole talk when it was ready to my editor, Yuri Kurusa, and he also said he didn't expect it. So we will see. Now, if you are in ferroelectrics, you usually talk about small field and you talk about large field. So let's also do mechanics of ferroelectrics as small field and large field. So I started to talk about small field properties, and I illustrate what else in ferroelectrics. I illustrate phase transitions. The numbers in brackets mean the number of slides, or especially I will put slide number 2 to slide number 6 on this topic. Then I go to large field properties. This is kind of a little bit the usual stress strain curve ferroelasticity, but I approach it a little bit differently. Then I discuss bending strength. And I guess that 95% of you, if asked how to measure bending strength of PCT, you would give the wrong answer. So maybe you learned something from it. Then there is still some cracking ferroelastic toughening. In total, I will not need more than 20 slides and 20 minutes. So small field properties. Small field, actually, the way we do it means a field about 1/1000 to 1/10,000 of a large field, driving field. That means when we usually apply for a large field 10 kilovolt per millimeter or 1, for small we may apply 1 volt per millimeter. We measure dielectric permittivity. And then we already have a lot to discuss. We can apply the Rayleigh law, we can discuss reversible, irreversible, contributions from the lattice, contributions from the domain walls, and we can have a great time. Then we can have piezoelectric coefficient, and then we again go through the Rayleigh law and have all types of contributions, and we put the opens in, and we write tens and tens of papers. When we do mechanics, we would consider the elastic compliance. We would apply maybe 1,000 to 10,000 what we usually apply. Usually we would apply 100 megapascals, or we would apply 10 kilopascal. Now the problem is you cannot write tens of publications because it's actually very simple. All there is an interatomic potential. And there is, I think, a fairly unambiguous interpretation. So you can write maybe 2 or 3 papers, but suddenly you get a lot of insight about all this discussion up here. And you get completely new information which help these people who discuss up here. As you know, all this is of course correlated here. In mechanics, often instead of the compliance, we just discuss the Young's modulus. I call the Young's modulus Y because in ferroelectrics, E for elasticity is taken already. So when we measure the Young's modulus, the way we do it is we use resonance frequency and damping analysis. And this is an ASTM. So in mechanics, you often take a bend bar. You hit it a little bit with a hammer. You get this type of signal. A Fourier transform gives the resonance frequency. The resonance frequency gives the Young's modulus. Yeah, we have a very nice machine which measures up to 1,500 degrees C, but it's not that easy and you need some time to do it. So that is how it goes. Now, I put something first which you are familiar with. I give you first small field property in barium titanate. And so that you are familiar with it, I give you a paper by Eric Ross and his group. And so there's the permittivity of barium titanate like here. All right, you know it. Then I draw from drag and I draw in the piezoelectric coefficient. Apparently that is increasing at the Curie temperature. Okay, then I draw in the Young's modulus. There's a little bit of a shift of temperature. These may be different materials. These are different papers. These are different heating rates and so on. So don't worry about it. The same peer person does it. It fits pretty well. So where you here go up, in Young's modulus go down because the material gets softer at the phase transition temperature. And then here, the cubic phase seems to have a higher elastic modulus, goes from 125 to 190. So it's a clear signal, but still barium titanate, okay, well, it's not maybe so interesting. So let's do something different. We had been working on NBT for quite a while, made our share of mistakes early on and tried to find out new things. This is after the initial publication by Malte-Vögler 3 years ago, but this is work by Andreas Wohninsland. Now here we plot permittivity. I use NBT, 3BT, it's just easier to explain, but we can also do 6 or whatever you wish. So this is the permittivity. Here's the ferroelectric relaxer transition. It looks a bit more ugly than in barium titanate because there's much more to discuss. Okay, this is permittivity. Now this is piezoelectric coefficient. It goes down here at a ferroelectric relaxer transition. So here you can make a lot of models. What is exactly in here? There's supposedly a relaxer with polar nanoregions. And there are very nice techniques to get at it. There's high resolution TM. And you can determine local polarization vectors in the unit cell. That, of course, is destructive and is statistically not so robust, but locally you get very nice approach, but you don't really know how much volume of PNR do I have. I don't think you want to use a TM technique to find that out. So let's plot the Young's modulus. Now that looks quite different from barium titanate. So down here, this is actually pretty linear. In a single phase material, it's supposed to go linear down with temperature. Apparently here, we don't even have a single phase material yet. It's about here. If we measure to 800, I didn't plot it for you, will find it. So at the ferroelectric relaxer transition, it's very soft. This is actually a sharper determination of the transition temperature than permittivity or piezoelectric coefficient. At least I think so. And then you have very strange curves here. Now observe what I try to plot here. Here is permittivity, piezoelectric coefficient, Young's modulus, and there seems to be P and R. P and R. Volume, that must mean. Now this is a new curve. And this is the volume fraction of polar nanoregions. And it is at this transition temperature, it's about 70%. And then it falls off like that. At 500 degrees C, it's still 10%. So I seem to claim that is a simple measure to determine the volume of polar nanoregions, non-destructive. Now, how to do this? It's actually very simple because mechanics in the small signal, it's pretty simple. This is the geometrical model. Of course, you can argue about a geometrical model. I say that polar nanoregions are something like that. And there I have a bulk modulus of the matrix phase of the polar nanoregions. This is by Weng from 1984. This is the relation of the bulk moduli of the separate phases and of the composite. And you simply take this equation. There's only a single unknown. This is the concentration of respective phases. And then you can actually also compare this by an independent measure of polar nanoregions, which my colleague Petr Groszkiewicz does by nuclear magnetic resonance, because there, with his different satellite reflexes, he, to great accuracy, determines the volume content. This was small field loading. Now I come to far field loading or large field. Now, of course, here we briefly face up to the fact that stress is a tensor. So when we do this, we want to determine when is the point which domains switch. This is very similar like when does a metal yield. So you need a whole stress tensor, not just one component. So you could make an experiment under tension. Typically, we want to make in mechanics of ceramics bend bars. But Fett and colleagues did also torsion. Then you get a different loading mode. This is mode free. And only if you do something like this, you find the yield surface. This is an example for a soft PCT. This is the stress versus the total strain. You apply, in this case, a shear stress. You get a linear curve and you get a plastic deformation, which is the domain switching. If you do compression, it's already different than tension. Because in compression, you switch different variants than in tension, and there's a factor of 2 in between. And then this is torsion. Why do I tell you this? I come to that still. Kyle Weber, more than 10 years ago, built up a machine which had a mechanical load frame. He put it into a furnace. He put 2 LVDTs on it. Even our metal physics group sometimes wants to use it. And then he described ferroelasticity. That had been done before, but not as a function of temperature or not to this detail and not the small field loading under stress. So you apply a load. By the way, he insists on if you have compressive stress is by definition a negative stress. He insists on plotting this downward. Some people still plot it upward and say, okay, it's a negative stress. Never mind. There's a coercive stress, which marks the switching stress. Then all domains are switched. Then you are linear elastic again. You have a different Young's modulus. You have a maximum in strain. You go back elastically. You have reverse switching. You have a remnant strain. There's also a paper describing mechanics of lead-free specifically. Now, this looks like such that at room temperature, this is the curve. If you heat up, the polarization is reduced, the non-cubic distortion is reduced, you get less of a hysteresis, less of a remnants until you are in the cubic state and you get a straight linear elastic line. So these are the effects you get. This was actually first described by Chaplia and Greg Harman more than 20 years ago, but this is the description for PCT multilayers. There is, of course, an interaction of mechanical field and electrical field, such that I want to show you here the unipolar curve, electric field versus strain. I apply 10 megapascal, it's like this. 20 megapascal, I push everything down further, but with the electric field, I pull most of it up again. That means there is an optimum stress for strain in D33 to get the most strain and to get the most piezoelectric coefficient out of it. That's one of the reasons why you run an actuator under a mild compressive stress. Now I go back to this, what I told you before, the curve of strain is different in tension and compression. Now we come to a considerable problem because a bend bar has tension on one side and compression on the other side. Usually a bend bar of a linear elastic ceramic has a neutral axis where there's no strain in the center, but here the neutral axis is not in the center. That's quite screwy because that means there is a usual linear elastic bend bar plus there's a plastic strain due to domain switching. So when you think you have calculated the tensile bending stress, in reality for unpoled or poled is considerably lower. Specifically, let's say I have poled, I have 40 megapascal bending stress, and then but it's really 0.65. 0.65 times 40 is 27 megapascal. So you think your material has a strength of 40, but it has 27. So this is then an example on one of the new K&N materials. And this is work by Yingwei Li from Wuhan University. Now this material has this type of stress strain curve. Let's only look at room temperature. Room temperature starts to have a nonlinearity at maybe 40, 50 megapascal. Now I measure now in a bend bar the strain on tension and on compression. And I plot the whole curve, strain versus stress. And this is the linear elastic one. And this is the true one. So what you do when you measure a bending strength and you put in the usual equation, you really only say, okay, it has a certain strain here. And from there, you really go up and say this is the strain. Then you think it's linear elastic. You think this is the stress, but in reality, this, of course, is the stress. So that's the mistake you make. Now, the strange thing is that for lead-free piezoceramics, and I think strength is a very fundamental property for anything we want to put into application. To my knowledge, there's not a single correct paper to determine the bending strength of a lead-free piezoceramic, and there are only very, very few correct papers to determine the bending strength of PCT correctly. It's quite disturbing to me, but so this was bending strength. Now I go to fracture toughness. Fracture toughness, this is quite well known. It's known from here. There's a toughness anisotropy. Yingwei gave me this. If it's unpoled, Then we have an equal distribution of polarization vectors. We put an indentation in and we have equal cracks in all directions. If it's poled in this direction, this is the distribution of polarization vectors, also like that. But if you have it like this, then these cracks are shorter. This is actually very well known. Now, allow me to explain how I want to recommend how to determine fracture toughness. The ceramics community still struggles with it, but there's an ASTM. This ASTM describes surface crack inflection. You put a noob indentation, polish away the elastic plastic zone and get a crack, which can be completely mathematically described. Also, you can take this geometry, or you also get a perfect crack from a very sharp notch. But in the end, this is a so-called long crack. So it has less utility than here. Now, ferroelastic toughening goes like such. This was described by these mechanics people who are also very, very good in ferroelectrics. So this is quite well known. So here's the crack. Then we apply a stress onto it. What is drawn in is the orientation of polarization vectors. Then there's the stress field. So they're switching in the stress field. And then we get a process zone. And this process zone is additional volume in the direction of the tensile stress and puts compressive stresses perpendicular to the crack plane and causes ferroelastic toughening. These are the toughness values we have measured so far, and we found in the literature. And I want to compare the fracture toughness, but mostly only of these techniques. Now, this is an ASTM. This is a very sound technique. I know there are techniques which are not quite so straightforward. They give a lot of room for interpretation. In short, are quick and dirty. PCT has a fracture toughness of unpoled or poled, maybe 1.0, 1.1. K and N, similar. BCT, BCT less. NBT, BT, 50 to 80% more. So this is actually an example that a lead-free material is much better than a lead-containing material. So for mechanical loading, I would advise to take this material, and these are the references. I said that by 17 I will about finish. I said I will finish in 20 minutes. I'm not quite making it. The conclusions are such. I think the small field mechanical properties help in rationalizing the microstructure and the electrical properties. The domain switching from a mechanical field complements the understanding from switching under electric field. For example, we have sometimes collaboration where groups develop new lead-free piezoceramics, but they are so conducting they cannot assess domain switching. So you can use a mechanical field. The ferroelastic behavior demands a complex evaluation of the fracture strength. If you measure K1C, you need to take care of fudge-free parameters. A fudge parameter in mechanics is typically a Greek parameter you use for a technique where you don't quite know what you're doing, but you can write a quick paper in it. I'm sorry. NBT-BT is tougher than PCT, KNN, BCT, and BZT. This is the research group. Andreas is working on small field. Wawa helped me with the talk. Yuri was the editor. He told me what I should take out and what I should take in. Thank you to all these. Thank you to the others. Thank you to you all.